megaya, la bemonani, lega do, atona bin mega bed megaya, la bemonani, lega do. Ando yake, logoroma kumaya, tinatiwanini. Ando sweetheart, logoroma kumaya, tinadokpere. Nagajini wajani mara, Martin de Tenania. Nagajini wajani kena, Martin de Wegania. Nagajoni wajani para, Martin de Wegania. Nen Polani mano wego antina derchan. Nen Timmy mano wego antina derchan. Nen Polani mano wego antina derchan.
They're not experts in culture.
Timmy mano wego antina derchan. Bin megaya, la bemonani, lega do. Atona bin megaya, la bemonani, lega do.
This is the
Megaya, la bemonani, lega do. Atona bin megaya, la bemonani, lega do. Bin megaya, la bemonani, lega do. Atona bin megaya, la bemonani, lega do. Swing my tioni, pila pera, tiono atamayina ye. Pila pera, swing my warani, pila pera, warano atamayin keken. Pila pera, swing my marani, pila pera, marano atamayina ye. Pila pera, swing my furani, pila pera, puro.
Okay, that was anyway, culture is culture. Good evening, ladies and gentlemen. Engineer Michael Chol is my name. I know I've been on this platform for some time. I've taken some time. I think there are a lot of things happening at workplace, and so couldn't get time. Today I decided to just share some knowledge on something that I was trying to do. I did a review of a design of portal frame box culvert. These they're a bit different from the normal traditional box culvert we design. This one, they are like U-type. You have bottom slab cast in situ. Then the vertical walls and the top slab will be they are cast as one, and you design it as a U-frame kind of. Model it properly with a pin support at the bottom, where the bottom of the vertical walls are treated as pin support. So all that you need to take care of. So it's about analysis and design of a 2-cell portal frame to alleviate flooding effects along a national road network. Of course, engineer my MJ, that's Michael Jackson. Chole is my name. Currently, I'm bridge and structure specialist in Yondra. As you're aware, Yondra now, by law, I think is going back to the ministry. We do embrace the plan by government to save money and to get back the entity to the ministry, the mother ministry, so that they work as one. Then I hope there's going to be synergies. And then the bottom line is, one focal point is, and the goal we have is the national road network, to improve the life of people by improving the level of service of our roads and bridges. So that done, we shall take it up and see how best can be handled. I'm a registered engineer with the ERB and also a member of Uganda Professional Engineers Institution of Professional Engineers. I also did a project management professional from PMI USA. Now this abstract, this report represents the analysis and design of a 4x3. Actually, the width is 4. The internal span, wall to face of wall to wall, is 4 meters, and then the vertical height is about 3 meters to the soffit of the top slab, which in this case they are all precast. Now the in situ today is good. The in situ for this is a separate slab. You will see from the model It's a separate slab that they do as a regulating slab to now receive the fill for compaction and other things. So the total length of the culvert is about 20 meters. There is going to be 2 cells, so with a separation of about 100 millimeter expansion joint. The culvert is designed to handle Eurocode traffic loads with a fill. This one has actually the fill vary from 0.5 in some location up to 3 meter cushion fill, which is the soil overburden. But of course, for this demonstration, I've decided to give a 3 meter, but again, I'm going to give a comparative analysis between 0.5, the 1 meter, the 1.5 up to 3.5. You're going to see as we go down, the variation in the axle load as the fill depth increases. So basically that, and then I think we have the in situ top slab is about 300 millimeter thick, and then the walls, the precast top slab, the side walls are all 400. Now the bottom slab is also 400, but I think with the review you can see this variation in depth. The variation in depth you see from 400 to 450, from 450 to 600. All these are the trials to take account of high stress or the shear stresses at the bottom of the vertical walls. You see at the bottom of the vertical walls, the forces are higher, and therefore they require a bit of thicker bases thicker base to absorb that punching shear, the shear stresses, and other things. So that's why you see this variation. Now you'll see in the model. The top slab and the walls are specified to be, I think the grade given is grade 40, while the bottom slab is grade 30. It's cast in situ concrete. The modeling and design were performed using Midas Civil and load dispersion for the traffic also load is also calculated using Excel spreadsheets developed by Davis Childs. Many of you who have access to most of this Excel, you know, we have one prominent professor, that's Davis Child, which does develop quite a number of those spreadsheets that we always use to help us with those design. Additional loads due to live loads, surcharge, and hydrostatic loads were also developed. As you are aware, gentlemen and ladies, when you are for culverts, it's a very simple loading that you need to understand. Culvert with cushion or with overburdened soil, you have 2 cases to consider. You have a case when the soil is dry. That means you calculate the overburden stress, the vertical stress on the culvert based on dry density. Then you're going to work on the lateral pressure, soil pressure on the walls based on the dry density. And then after that you do the surcharge, you do hydrostatic separate. Okay, hydrostatic comes in now. When we're dealing with hydrostatic, that's when that moist or the saturated situation comes in. That means now you have now case 2. In case 2, you have the overburdened soil now has a saturated density. The density for the lateral soil pressure will also have the saturated density. So you need to have the 2 densities so that you compare and you look at worst case scenario. And also the issue of hydrostatic pressure comes in. And also if the traffic is on top of the bridge, then definitely you have both the dispersion effect. If the depth of the fill is above 0.6 and above, then you should know that it's no longer rolling loads. Or the tire or the wheel load is now you disperse it and you get patch loads, which now you design as static. But for anything less, then you can now model it to have the lane loading, and then the traffic it will run, and then it will give you the traffic load. So that is something you need to basically as simple as that. The rest now, the box culvert you can design using hand, because box culvert are considered as rigid members, and so issues of fixed support and the rest of it, you should be able to handle that. So this is an internet of portal frame that I think I put in here, but I'm going to modify this. This is same thing, but I'll do AutoCAD drawing and other things so that I beautify this more, and then have other, when I'm comparing now the effect of when the fill is 0.5 meter and then when the fill is 3 meters. For now, we are dealing with 3 meter depth. But when I'm dealing with a fill of 0.5, then I will try to do a bit of adjustment, but more or less not similar stuff. The introduction here, basically, we are all aware box culverts are essential structures in civil engineering. They are used to channel water under roads, under railways, and other embankments, and in low-lying areas where we don't have proper channels, channelized water. Where you have proper channels with well-defined river bank or channel banks, it's difficult to do boxes, because now this is where we begin to look at the score depth, turbulence flow through, and that becomes so. Box culverts and other culverts, they are basically dealing with water which is more still, stagnant, and can flood from any direction, and so it acts as relieving structures. So this is so basically you find that they are used in most of the swampy areas, areas which are low-lying and the rest of it, but not well-defined rivers with turbulent flow, which require a bit of in-depth assessment. This report details the design of a precast box culvert, considering structural requirements, material specification, and load impact. Precast in the nature that I think it depends on the contractor or the designer, and also the agency of implementation is very important. Like this project lies on one of the critical roads, northern corridor roads here, and so every minute you stop trucks or traffic, you are generating about 1 kilometer or 2 of jam, and so the accelerated construction implementation should be key. And that is why you see the choice of coming up with precast. Precast means by now, when works commence, when you are doing mobilization, the design is done, everything is done and approved, you commence the prefabrication of those portal frames. Now, once you are done, then when the setting up is done, you just go to site. The critical part is to locate the structures, do your rock filling, level it, stabilize it, blind the foundation, and put in your concrete. Once the concrete is done, the next is placement of the portal frame, which in 1 or 2 or 3 weeks you are done. Then what delays now is the cast in situ of the top slab, which tend to tie which tend to stabilize and distribute load and also tie. That's the in situ slab that you use to receive now the overburdened soil. So basically that's what we need. So here now under design methodology, the load calculation, we have the dead load. Dead load normally you notice is the self weight of the member which you are putting. Then also additional dead load, some is and the rest of it. So in this case we have I've already explained the soil, the field, both dry and saturated condition. You need to take note of that. Then live load, we have the traffic loading, the LM1 tandem system, LM2, and then the LM3. These are some of the loading that you will apply. But also remember that there is a manual which is used for design of box culvert. I'm going to get that and share. It says PD something 64. There's a manual which also they use for box culvert. But in event that you don't have that, you still can use this, because these have got very good axial load that tend to help you to disperse this loading on your design. Like LM1 tandem system, you have a 600. You have a 150 axial, you have a 100 axial, and you have two. We have 300 axles, 200, and then the 100, which wheels come to 150 as per the tire load or wheel. Then you have the second set is for 100, and then the third set is the 50 for the wheel. And in total you get 600. Then for LM2 you have 400 axle load. You split it per tire or per wheel, you have 200. So that also, in a way, if you compare with the British standards, we have what? We have we have 450 as the axial load for the highest, which comes to about 112.5. That is HB45. So definitely you begin to compare. So when you use some of the things, you should be able to get some worst case condition that give you a good simulated structure to stand the environmental and traffic load. Then the live load surcharge, this one comes from the traffic, overlying traffic on the side of the walls. Then hydrostatic loads, which pressure from water flow and accumulation of the side walls and top of the culvert. That's why you have to look at two conditions, dry condition and the saturated condition. Please don't forget this one. Very important when you're designing box culvert. The rest is okay. Materials here, we already talked about material, concrete and reinforcement with all their grades given. So you have a class 40, then we have a class 30. Okay, this is cylinder 32 and compressive 40, cylinder 30, compressive 37. Definitely these are indicative. When you do mixed design, you'll be able to get that. Reinforcement, they're using 500 MPa. Then modeling finite element analysis conducted using Midas Software to determine stress distribution and also deflection. Shear and moment calculation, ensuring the structure can withstand the applied loads. So basically, the output of your modeling, loading, analysis, you get the outputs. Which output gives you the shear load, the shear forces, moment, axial loads, and others like other stresses. You are able to get that. Now it is now these outputs that you now translate into the next stage of design. If you have to now use some tailor-made the code of practice and other thing, now you can now go, because you know the moment, you know the shear, you are able to get the shear reinforcement, you are able to get the amount of reinforcement. You first try, you do the required, you get to know the required area, then you get maybe it's not passing some of the limits or requirement, then you improve until you get the area provided that meets all the requirements. So this is so now at the analysis you get the value, which value now are taken into the design stage. For this matter, since you're using Midas, there's another stage where you do the design. So we shall see how that is done. So this is what you have, the thickness of the top slab, bottom slab, all provided there here. When you look at the top slab, we are giving you 400 mid-span 450 support. These are now the section that tend to, which I think we have tried and they were passing well, the moment and the shear. You see the moment tend to be more in the middle, but since it's fixed support, sometimes the end support or end moments tend to be higher than the mid-span moment. So you need to be aware of that, and you do your design and detailing accordingly. Then the bottom slab, you have 450 mid-span and 600 over the support. That one also you need to be aware. Always at the support location, please try to double check and double click. Now the load dispersion calculation, here we have used Davis child because it's now exceeding 1 meter, and then we are able to. And when you look at this table, I think sometime back I shared this table, you will find actually that this higher value here, you see the 204, the 153, the 106, and then coming down here. These three are actually telling you that at the depth of 0.5, you have a very high value of dispersion forces or pressure on top of the slab. Then at 1 meter, it's dropping. As you go to 1.5, it's dropping further, up to about 3. At 3 is actually you have dropped to only 26 from 200. So you see now there's a point where the traffic load becomes negligible. But at the same time, if you see this rising member here, this is now the effect of the dead load. So this, as you increase the thickness of soil, you are increasing the dead weight and the effect. So the moment, the shear, soil pressure, everything start increasing with the increase in in the overburden sizes. So it's 0.5, you go to 1 meter, it's increasing, but the effect of the wheel load is also reducing at the same time. So there's a point now where you find actually you don't need actually to consider traffic load in your design of box culvert when certain depth of fill has been reached. So this is a very good table. You can look further. And so we are saying figure 2 indicates effects of increasing fill depth on top of box culvert to guide the design. Note 1, as you increase the depth of cushion from 0.5 to 3 meters, stress due to axial load reduces to minimum, and the overburden soil pressure increases with depth of fill to maximum. So basically, you need to be aware of that. So if you have pipe culvert near your area and you find someone is trying to just cover the culvert, just temporary covering so that people can use to cross, then they want to resume work like tomorrow. It's a very risky approach. By the time the road work is done, that is why sometimes at commissioning we find culverts have cracked, because you have exposed your culvert to traffic during construction in the name of allowing for diversion or quick access or crossing by the public, not knowing that actually when you have less fill, the weight of the truck goes directly on your culvert, and definitely if the culvert is not protected with concrete surround, definitely you're going to have a problem. So sometimes you can see some contractors, they do concrete surround. They will tell you, for us all this, it's okay. We are going to cut. You don't know why, because concrete is very good in compression. So when you do that, and then you have a 0.3 to 0.5 fill, just temporary to allow nightfall and then traffic to use, or tomorrow you resume work, whatever truck which is using crossing your culvert will not damage it. But for us, some of us who just do the fill using soil, you continue without inspecting, but the culvert's already cracked. So we have to be very, very careful with that. So note 2, comparing EN loads, it is noted that load model 1, including tandem system, develop high stress on top of the culvert, followed by load model 2 and load model 3. Gives lower stress on top. You can see it up here. So these are load model 1, giving you those higher value, and then load model 2, and then load model 3. They are here. These 3 here, from 100, this 106, 153, and 20. These are the load model 3, load model 2, and load model 1. The same applies as you move here and then decide that 33. Okay, fine. So normally you say, I'm using SV196, blah, blah. Please try to check all and make sure even load model 1 is done, load model 2 is done, so that you are able to get worst case scenario for your design. Reinforcement design, this one I think came from our analysis. Basically, we are not going to dwell too much. Top slab and walls as bottom frame in linear measurement. Reinforcement to handle bending moments and shear force. This is the traditional way. We know concrete is weak in tension, so reinforcement always is brought in to take on the stresses resulting from applied loads, the fill and then the traffic. So that is what you have here. You have the bottom slab, you have the top slab, the bottom frame, you have the wall and the top slab, which is giving you here the support area, the mid-span area, and then the ceilings. So very interesting ceiling. The issue of ceiling, I want you guys to read a bit of ceilings in the slabs and the rest. Is a bit very interesting, and we always struggle with the young engineers. How do you detail it? So look at the detailing pattern and try to see local. You will try to go to internet, and I'm going to share more, and you'll see not now. There's a way you look at it, and what is the length where your shear links are required. And then in between what is required for normal. You get it. So these shear links, they work everywhere, in slabs, in foundations, in big walls, and the rest of it. So it's always good to check. For construction now, I may not waste too much time. I've already explained where you do your foundation. You prefabricate the bottom frame in your yard where you have worked on it. You have prepared everything okay for steel formwork to give you very good quality portal frame, and then the rest of it. So your precast sections you manufactured off-site and transported to the site with the low bed properly protected to avoid excessive vibrations to create crack. We don't need crack initiation at construction stage. We don't need cracks. Will only come from the loading, which we normally do take care of during that. So these are the sizes. Then placement of precast unit. They are placed on the in situ base, so that you must precisely, correctly construct your in situ foundation. Once you have done that to the required fall or grade, because please be mindful that you have inlet and outlet. So the inlet normally tend to be slightly higher. If it is 0, then we have a negative, maybe slightly of 0.0, maybe 2 meters down or 20 millimeters to the at the exit point or something. But it will determine. We have manuals for the drainage and the falls and all that are all given. That one you always don't forget. You must be aware. In situ concrete topping is also allowed. In this case, it is given. Foundation construction follows the same process and principle as a normal box culvert, where you do you remove the weak soil. Remember to have done some DCPs to know where is the refusal for you to start filling the rock to avoid rocks disappearing in the weak soil. So once you remove the agricultural soil, then you are able to fill. After you have filled, roll it properly, level it, do the blinding using those crusher runs and the smaller aggregates, and then from there you start your foundation works. So that is very, very important. Now there are two notes here that we need to know. When you are dealing with box culvert, and I always see people rushing to put breaking loads, put them on. No. The researchers have already done something, and they have discovered that actually temperature effects on box culvert which have cushion is when the depth is about up to 1.5. You can apply your temperature load, and also the traction or braking load also become negligible once the depth exceeds 1.5. So once your depth is more than 1.5, then you just do your normal traffic load. Remember, it's already reducing. Even the traffic load is reducing, but at least you can apply that. You don't need to now put in your traction or braking load on your culvert top of the frame. You don't need to apply the temperature because it's cool 24/7. And so we don't. But with the if the depth is between 0.3 to 1.5, please, you can do that. In conclusion, we are saying this report outlines the comprehensive analysis and design of a 4x3 portal frame precast box culvert with 2 cells and a 3 soil overburden. Please, portal frame, keyword, portal frame, precast box culvert. A box culvert is a box culvert, but now this time that it is a portal frame, the U-type, and precast. So think about prefabrication, the yard where you have to do that fabrication, the mold, the steel mold, the processes required, even the grade of concrete for prefabricated stuff tend to be. Even the lifting effect. You may need additional reinforcement to take care of lifting. Supposing there's an impact somewhere, what happened? So mark this word, portal frame precast, and then 2 cells with a separation, and then the overburden of 3 meters. Considering all relevant factors such as material specification, load impacts, and construction methods, the design ensures the culvert will perform effectively under the specified condition, providing a durable and reliable solution for water management and transportation infrastructure. The design was carried out in accordance with Euro codes. Okay, so here is a model. So you can see this model has what they call spring constant at the bottom. All this you see, these are, the in situ is only the upper part here, and the lower one down you see. The rest are precast, and we have used 1 meter strip. That's what we need, and this is a typical section. This is a typical section here. So you can see the bottom with the spring constant simulating that, and then this is slightly thicker because of shear effect. Now we would have tapered this, but Midas does not design tapering sections. We raised that issue. I hope they will handle that. and then you have this red, this top, this part here, the green part here is now the in situ, but this one here is the portal frame. So this portal frame is 4 meters here and 3 meters here. This is a gap of 100. So this will be filled up with some of this filling stuff that the contractor will consider, and then you load this structure, you fill it up by around 3 meters. You have effect on the sides. So there should be some shear keys, especially for these members, to avoid this. Remember, if you calculate the shear here, can actually push this thing down. So this has to be rigid. This area has to be rigid, and this frame must be rigid up to down to avoid being pushed by lateral soil pressure. And how do you do that resistivity or resistance? Is to introduce shear keys at the bottom. That should be able to help. So that is that, and this is a line. This is a line diagram of the two portal frame, giving you two cells and the bottom in situ slab, simulating the soil pressure with the spring constant. And then here is the same model. Now this one doesn't have, this is a 3D without any top slab. So this is what we have, because that the construction process is you do this bottom slab, then you place this one, and then later on you do now this last one here, and then you will be done. Then the wing wall comes later. These are typical sections that we did. This is now the model. This is the analytical model for plates, bottom slab, the top, and then you have your normal portal frame, which I think somewhere you're going to see. You can see here. This is this one here. This is the normal portal frame, and then you can see them. Because if you try to look, if you consider opening as plates, then this will be deactivated kind of. You see like line, because these are beams. So when you open, when you go and view the model as beam, then you again you are able to see this, but you're not. This one goes into a bit of which is not very clear, because get deactivated while the other is activated. So this is the model, and this is the output. This is the shear, and this is the moment. So you can see that all these moments are for 1 meter. 1 meter. If it was a normal plate where we have the walls all the way, you just have to cut a section to be able to see. But now this is, now you can see this is the frame. So the plate, which is the bottom, become deactivated kind of. You can see the pattern, and then so this is a 2D. You can see that where you have the portal frame resting on the in situ base slab, it is pin support. You have to be careful when you are modeling this. When you are modeling this, you have to go to let me see if we can have it. You go to your to the beam releases. From the beam releases, you are able to, with that this aspect of pin support, pin to fix, and fix pin. Now this is what you do. All these are fixed except this one is pin, and then the rest will be fixed. Once you do that, you will not go wrong. It will give you that pattern the way you are seeing it, and you are good to go. So this is shear, and this is axial load. So this is now the axial load in 3D, and this is now the boundary condition. So this boundary condition is what you need to. At the bottom here, this is where now you are giving this support not to take up moment. This one don't take moment. That's where you have to go. These are frames. These are portal frames, by the way, 1 meter. So if you do as the walls, normally there's a bit of difficulty in putting that frame, and putting the boundary condition. But if you do as portal frame, you are good to go. You will have it well. So now these are the rigid links, which we have it up here, which is connecting. We would have done this one is elastic. You can use elastic link, but there's where you have to define it as rigid. It will still give you similar thing like using rigid links. But down here, these are support system, support condition, where now you are connecting it, and then also giving the definition that this last point is a pin point. What we have to connect the pin point together with the slab, so that it communicates and the load are transferred, as you will see below. Yeah, so basically that is what we have. And so here is the thing. So here is your slab, bottom slab. Then this is these are the elastic links, which are rigid links connecting the in situ slab to the top here, so that there is a transfer of load in accordance with the way it acts in reality. Then down here also you have the support, the links, but the point of the last point has to be, this point must be defined as pin. So this pin end, and then the next joint will be rigid, and that's how you see it down here in the 2D of the impression. So basically that is what you look at. What I forgot to do was to demonstrate the loading, the different loading, which I think I will do for the other one. So this is the 3D. This is now the portal frame as to lay it. This one is one member made already. I've done this and used the average, because if you do tapering and you indicate here, it cannot design for you. I told you that Midas will design basically rectangular member, not a tapering stuff. So ladies and gentlemen, this is your modeling up to the last point. I've gone slightly down, but the outputs are here. These are outputs. So from this output, when you are done with all this modeling, I told you that in Midas there is a component of design. So you go to the design component, and then you are able now to do your specifications, all the design code, the materials grade, the limits, the stresses, crack width, all that you have to specify. And then once you have done all that, then you are able to run. But there are also procedures. I think we shall get time and demonstrate. But in my previous thing, I think there's somewhere we did something of design of box culvert. So it's not very far. Once you model it and you've given the right boundary condition, it should not be a problem. So when you do your design, this is what comes out. So you find these are the top portal frames. You see this one is near the support. I want you to take note. This one, you see more reinforcement here, and less. This is mid-span. So that means the moment tend to be more at the support than at the mid-span. I'm taking you back here. So if you look at this moment here tend to be less than moment over support. The rate value seems to be high. So that is what I'm trying to say, that it tends to give you less. And then shear tend to be higher here, but reduces to 0 mid-span and increases. So the shear links may not go all the way there. So this few distance you need to know for you to be able to specify, and then you're able to do that. Okay, so basically in the design report, this is what gives you. It gives you so all the details of the enforcement you need to do. They're all captured here. At your free time, you can actually do that and try to view, and you look at it and you appreciate. Then these are all. Then there is for vertical wall. Then there is for the top slab. This is for the top slab portal frame, and then you're going to have for the bottom slab. And then you see this is like a column. So you can see the PM interaction diagram comes in if it is a what. So you have a design, you have applied load, you have axial forces and moment resistance checks. So they go and look at the worst case, and then the shear force resistance checks also done here. All have passed. Now here you can remove, when you're modeling, you can remove these two middle bar. Very easy to model, to remove it. We shall demonstrate sometime back and you get it. Then when it came to, this was for the summary. Normally for Midas, you can look at summary to avoid going into detail output. There's detail output, then there is summary, graphic. So here is graphic. I just decided to give you graphics, and then also graphics for that. But now for the slab and the rest, they were giving detail. So with the detail member, it gives you domain, bottom and top slab, bottom mid span. So it gives you the member information, the Euro code, everything. Then you come down to reinforcement that has been input to design. The thickness is given, reinforcement data given, distribution bars given, and stirrups also given. So you find it gives you everything, the spacing given here, the cover as you have specified, because you have to specify all the cover, everything. So that gives you, and then now you start with moment checks, moment capacity check at the negative. This is now the one at the support system. It gives you all the parameters, the design parameter all given here, and then you find that it's telling you that actually your design basing on the reinforcement you have specified, they're okay. Then moment capacity for positive, that's the bending moment, is also here. You look at it, it gives you the same thing, it has passed. So that means the reinforcement you have specified are okay. You come down and check then the shear capacity, you have to check and then make sure it's okay. Even the stress, checking the stress limit, concrete, negative characteristics and the rest of it. It has to check for you the crack and the stress limit, and then if there's any problem, then you are able to go back and modify. Even checking on crack limit, they're all given. So you go, if it all have passed, then mean you're able. Look at the ratio. If the ratio is quite low, less than 0.5, that means maybe you can still adjust reinforcement so that you can go slide on a 0.75 there, and you see, because again, if you do too much low, it means you have over design. So we have to strike a balance for value engineering and see how best we can handle that. So this explains many things that did there. You see now, this is the second one. The member name is domain, bottom and top slab, bottom hogging. So it will explain for you and give you all the details. So they are similar. You get this one, this is the bottom detail. This is where the thickness has increased. Let me see. To 600. Because that means that the 400 couldn't work. So now you can see from the model, it is 450 to 600. So that's how you can see now. It has given you that one. All these are designed from Kong and Ivan, Mosley, and then other code of practices and literature. I think they follow this procedure, and you're able to get all that. So all these members are all designed. See now, this one is giving you mid span of top slab, which is about 300. Now this one is now doing this in situ one. Is designing for us the in situ. So it has given you all that, and they're saying it has passed, but I believe I need to check the in situ again. These bars could be more. We need to reduce the amount of bars for the in situ, not the portal frame. So this one is for the, so every memo you have specified will all be calculated for you. Your work is to organize it and pass it on to your CAD engineers to do the detailing. Once you have done your detailing, you do your takeoff, prepare everything, you check that. And also remember, all the design must be quality assured by another senior person or someone equally expert like you to check, so that sometimes we make mistake, you easily forget something like factor of safety or the loading. So you get that. So basically, this is now basically output. The most difficult part is the modeling. From modeling, then you come to loading. Once you get the loading ready, I told you for box culvert, be mindful of loading in two conditions, wet conditions and dry conditions. Consider all that as different cases. You will get the worst case scenario and you are able to get it right. So I think that is that. So portal frame is a bit interesting. We shall share more. I will now, next time I will explain for the 0.5 meter cushion. I think I will explain not the output. I will explain the Midas, how I've done it, and then you are able to do. Remember please that we can also as well do construction staging for this. Is a very interesting candidate for construction staging. You will do your first, the bottom slab as construction stage 1, then you do portal frame, then you do boundary conditions, then you do the top slab, and then after that you give it now your 10,000 days, after which now you can now apply loading. So I think we shall also try to do that, but that is how you can handle that. So with that, I think I call it a day for now. We shall continue to share knowledge. Fortunately, I have to declare here that from the time I started to date, I think I have over 15 young engineers who are following me. One came, I think, on Wednesday to our head office from Ministry of Works, and then she said, I got your contact from YouTube, And immediately I called her. I said, come. I took her through. They had given her to design a 20-meter span bridge from somewhere in northwestern Uganda, in West Nile. So I explained to her, once your boss has said you do a design of a culvert, no, or a bridge, you now go back as a designer. You are almost a team leader. You're a coordinator. You start to look at the processes required. You don't jump to start opening. Your Midas come at the tail end. You need to look at the data to be collected, the team to collect the data, the sequencing, everything. So I was a bit impressed that young people are trying to follow, and I do encourage that for some of you. If you have some young engineers who would like to follow what we do, please, here is where we share our knowledge. And I would say thank you so much, and God bless you.